So this is not possible. I'm sorry, I think I tried reading an SMS and then I had to now log in back to the system. Oh. Okay. So I was explaining that in telephone exchanges, what they do is, now there are, let's say it's a 16 lines or 32 lines telephone exchange. So these are how the standards T1, T2, T3 are developed. That there is a T1 link. A T1 link primarily perhaps carries 32 telephone lines. And 32 telephone lines means that, so 32 telephone lines. Dr. Ali, perhaps you are sending SMSs, but if I read that, I'll have to stop the automatically perhaps stops that. So I will try to just keep ignoring messages. And so what it does is that there are 32 telephone lines, okay, which gets to a T1 link. It takes sample from one line, then sample from the other line, sample from the other line. So it repeats 32 and then it again. So sample from first call, then sample from second call, then sample from third call, and it keep doing sample from the 32nd call. 1, 2, 3, 32nd. Then again sample from first call, sample from second call. So this telephone exchange now has to pack 64 into 32 bit per second. So it increases the amount of information that is going through a T1 link, and then T2 link successively put in more, and T3 link puts even more. So try using Messenger, it would not interrupt the live session. Okay, I will. So so here is how the telephone exchanges work. But the important aspect of decimation is to be remembered, that decimation, if you intend to do decimate, you must and for that you are doing to reduce the cost of the system or to remove some noise. So we always first pass our signal through a decimation filter, pi over m filter. And then you decimate it by pi. So very simple. If you intend to reduce the sampling rate, may it be images or voice or any other signal, you go through this step. First you observe, plot the spectrum, and if you find out that once you are plotting the spectrum there is nothing beyond pi over m. So if there is nothing beyond pi over m, then if your spectrum of x exponential j omega is 0 for pi over m omega is greater than. So this is a relationship which says that, look at your spectrum. If your spectrum is only up to pi over m, then you can simply throw away samples. If not, and mostly this will not be the case, if not, then pass your signal through a pi over m filter. Pass your signal through a pi over m filter. Once you pass your signal through a pi over m filter, only then you can decimate. So we have an example which perhaps Dr. Ali might have already run it to you, but if not, then I'll show you the example where we have voice and we want to decimate. Voice is sampled, then we decimate by 2. So before we decimate it by 2, we pass it through a pi by 2 filter, and then you decimate. So this is the decimation. So decimation is done like this, that you pass it through a filter and then you throw a sample. No matter how much you intend to decimate, it's up to you. But always, whether it's an image, otherwise you will lose some of the information will come back in alias and will further reduce the quality of the signal, which we never want to happen. So this is the the decimation. Interpolation, as we started learning about interpolation, is reverse of decimation. And in decimation, you are losing information. Remember, whenever you decimate, you got to throw away part of the spectrum. So you lose information. But once you are doing interpolation, you don't lose information, but at the same time you are not adding any information. In interpolation, there is absolutely no way to add information in a digital signal, may it be an image or a 1D signal, unless you have an a priori knowledge that it is actually, this image is about this, otherwise, or the signal is about this. Otherwise, there is absolutely no way that digitally you can add information into a signal through a process of interpolation. Interpolation merely that you have a signal like this, and originally based on the Nyquist criteria, you decided to sample it at some rate, which is good enough to recreate that signal exactly in this shape. But for some reasons, and I have told you the reasons, the reasons is if you are mixing the signal with another signal which is sampled at a high rate. For example, you are adding your voice into a CD quality music. A CD quality music is sampled at 44 kilohertz. So there is a music, and you are singing, you're trying to sing. So this is you singing. Or you are originally sampled at 8 kilohertz. Analog to digital converter, you are sampled at 8 kilohertz. This CD which you are playing from your computer is at 44.2 perhaps kilohertz. And you want to mix it so that mixing your voice, the singing into, but you cannot do that unless you upsample it to the same rate. Only then you add it to the music and play. So primarily interpolations are done primarily for these reasons. Usually that you intend to mix it with a signal that is sampled at high rate, and so you got to increase it. So you cannot really improve or add any frequency content. All you are doing is that adding intermediate samples. So this is also in signal processing. This is called redundant information. This is redundant information. Usually we don't like redundant information, and we always throw away this redundant information. And why you are adding by yourself? Because you are making it compatible with another signal to be added. So that's the only reason you do interpolation. And so interpolation is done in following steps. So once you are interpolating, so you have a sample here, then you have a sample here, then you have a sample here, then you have a sample here. Let's say you have these three samples, and you are doing interpolation. Interpolation, first you add zeros, 0, 0, 0. Let's say you are interpolating it by 4, 0, 0, 0. Okay. So first step, that you add zeros into your signal. So what will happen once you add zeros, okay, to the frequency spectrum? What will happen to the frequency spectrum? And we can actually easily establish the relationship of a signal which originally was this, and now once you have added zeros, it looks like this. So for example, this is a signal which is, you have x0, sample x1, you have sample x2, and you have sample x3. So its Z transform would be x0 plus x1 Z inverse plus x2 Z minus 2 plus x3 Z minus 3. This is what will be the Z transform, right? We know this is the Z transform. And then once you add zeros, and take Z transform of this signal with zeros. Now because the samples, non-zero samples, have changed their location, so the Z transform will look like this: x0 plus x1 Z minus 4 plus x2 Z minus 8, because now it is at 8, plus x3 Z minus 12. So this is, the relationship. So we can simply, looking at this, the Z has raised to the power minus 4. So if L is equal to 4, so if this is my X and this is my interpolated Xi, so the relationship is that Now my x of z is xi of z is x of z raised to the power l. So this is the relationship, that every z, once you insert zeros, every z is going to be a power of l, or the Fourier transform will be xi of exponential j omega is x exponential lj omega. So this is the relationship between once you insert zeros and once the zeros are not there. So this is the relationship between the two. Okay, so this relationship, if I try to plot a relationship where x, let's say you have a function which says y is equal to x, then you have a function which says y is equal to 4x. So what will happen? Let's see, y is equal to x. If you try plotting y is equal to x, it will be this. At 1, x1, y will be 1. X is equal to 1, y is equal to 1. So it is, this will be plotted like this. And now try plotting this. What will happen? Okay. Once you put x is equal to 1, y will be 4. Okay. So only if you put x is equal to 1 by 4. This is how it will be plotted. That now y interpolated 4x, once x is 1 by 4, so 1 by 4, 4 cancels out, you get 1. So this will be 1. So it is telling us that the x-axis is actually divided by 4. Once it is multiplied by 4 in the relationship expression, and on the plot, you need to divide the x by 4 to get to this plot. So same is the case for the frequency representation of the signal, that entire axis is divided by L. So if you are interpolating a signal like this, okay, this is a signal, that you have a signal which is from minus pi to pi, okay, and you want to insert a 0 after every other sample. So you have a sample, you put a 0, you have a sample, you put a 0, you have a sample, you put a 0, you have a sample, you put a 0. I think this is very simple, right? Just inserting 0 really is simple, that every other sample you insert a 0. So inserting 0 should not be an issue. But after inserting 0, if you again plot FFT, originally you see a spectrum like this. Once you insert, so the entire this, and we can do this in MATLAB as well, will appear like this. Now this spectrum would go like this. This pi will be now pi by 2 minus pi by 2. And there will be another copy, and this will be at 2 pi. So 4 pi, this will be at pi, and the 4 pi will be at 2 pi. So you get an extra copy in between. Inserting 1 0, you get 1 extra copy in the spectrum. Inserting 2 zeros, you get 2 extra copies in the spectrum. Inserting 3 zeros, you get 3 extra copies in the spectrum. So a very simple relationship. I can, just by knowing this fact, I can plot the spectrum of the two signals. For example, I give you a signal, and I ask you to insert 4 zeros in the signal and plot the spectrum. So I'm not giving you the digital signal, I am giving you its spectrum. I'm saying this is the spectrum of an original signal, and show the spectrum if you decimate it by 4. So closing your eyes, you should just draw 3 extra copies, extra copy, and here is 2 pi. So this is what? So this will be, this 2 pi will be 2 pi divided by 4. This is 2 into 2 pi divided by 4. This is 3 into 2 pi divided by 4. And this is 4 into 2 pi divided by 4. 4 cancels out 2 pi. So it's very simple, right? So giving you a spectrum, asking you to plot a spectrum where you have interpolated it by a 4. What if I ask you to interpolate it by 8? What will happen? That you are going to get how many copies? 7 copies. So if I ask you repeat the same question interpolating it by a factor of 8, what will happen? So you say, okay, 8, 1, 2, 3, 4, 5, 6, 7, and 8. So you make 7 extra copies. So interpolation, and this pi will be now pi over 8. And you can successively 2 pi over 8, 2 into 2 pi over 8, 3 into 2 pi over 8, 4 into 2 pi over 8, 5 into 2 pi, 6, 7, and 8 into 2 pi over 8 will make a 2 pi. So 7 extra copies. So simple that in interpolation, once you are interpolating a signal and you are given a spectrum, all you have to do is just make enough extra copies, and you can check this in MATLAB. It's very interesting that if you do this in MATLAB, and I think we should plan, Dr. Ali, a lab where we give them a signal, maybe voice, and ask them to interpolate that voice by a factor of 8, going through all these steps. So the first step is that after every sample of the voice, we have to insert 7 zeros, then a sample 7 zeros, then a sample 7 zeros, and plot its spectrum. And once you plot the spectrum of the voice with zeros in it, you will find out extra copies. You'll see all the extra copies in them. So we should do this experiment by interpolation by 2, then by 3, then by 4, then by 5, then by 6, then by 7. And every time playing that voice, after you go through the all steps, and you will find out the quality of voice will not change. Though you are increasing the number of samples, 8 times the number of samples, but there will be hardly any change in the quality of voice, because you are not adding any information, you are only adding redundant information that is not adding any value to the quality of the voice. So this is very important to really understand that interpolation, once you are interpolating, and I have shown you mathematically and I have shown you graphically that inserting 0 means this. Okay, so in order for this to be played, the zeros are to be lifted to get into the shape of the signal that we have discussed many a time. Like, this is the signal. Originally, these are the samples. Now we have inserted zeros. Let's say 6 zeros. So now they are to be lifted. These zeros will basically, if you play a signal with zeros in it, it'll sound horrible, because it'll play and then it'll bring the value of voice to 0, 0, 0, 0. So they got to be lifted. And lifting means that they got to be lifted to take the shape of the signal. In order to do that, as if they are originally sampled at a higher rate. A signal which is originally sampled at a higher rate will look like this. Pi over 8, pi over 8, 1 minus 2 pi. So what is the difference? Look at the difference. Now, the signal which is sampled at 8 times the higher rate, okay, 8 times the higher rate, its spectrum will look like this. A signal where you have inserted is looking like this. So what is the difference between this and this? That this does not have the 7 extra copies. So somehow you got to throw away 7 extra copies, and this is done by passing it through a low pass filter. You know, it's copy at every. So with gain L, if you do that, you get this. From here you come to this, and you got to obviously have this L. So in interpolation, to summarize, all you have to do is first you interpolate. Interpolation means add zeros, L minus 1 zeros after every sample. Then throw away all the extra copies which have resulted for you to. So these are the two operations which you need to perform. First, insert zeros and then remove extra copies, and that passing through a filter will bring the signal values into the shape of the signal. So this is interpolation. So decimation and interpolations are two operations. In decimation, first you pass it through a filter, and then you throw away sample. Okay, so these are the two operations. First you pass it through a filter, remove all the frequency contents which are not required, and then you throw away samples. In interpolation, first you insert zeros and then you pass it through a filter to bring the zeros to some values. You never throw away samples and then filter. If you are doing that, you will lose information. Remember that. In decimation, first pass it through a filter, remove all the frequencies you don't require, throw away samples. In interpolation, first you insert zeros and then bring the zeros to their values by removing the copies of the spectrum, passing it through a pi over L filter. Pi over D filter. This filter is called an interpolation filter, and this filter is called a decimation filter. I think let's take a 10 minutes break and then we'll come back and resume from here. Thank you.